Okay, so what we're going to look at today, guys, is some of the other applications of uniform circular motion. We talked about banked curves and unbanked curves quite a bit last week, but now we're going to look at something that's maybe not like practical in the sense it would affect all of us, but it's practical in the sense that it can solve some problems associated with, let's say, traveling in space for long periods of time, right? If you've seen any like more recent science fiction movies like The Martian, by the way, you need to read the book. The movie's pretty good, but the book is so much better. Okay, so if you haven't read the book for The Martian, totally watch that. Or totally read that one. But there's, in most of our kind of newer science fiction movies, okay, we have more practical ways of generating artificial gravity. Okay, most of the time, part of the ship does what? Spins. At least part of it spins, and that generates artificial gravity. That works. Okay, if we could actually build a ship, okay, that could travel from Earth to Mars and carry people, okay, it would definitely need something like that, or they would be in zero gravity for 6 to 10 months, depending on when they make the trip. Okay, and where Earth and Mars are in their orbits. That's a long time to be in zero gravity, because being in zero gravity has some pretty severe effects on the human body, because of course the human body evolved in a 1G environment. Okay, a lot of the things in our body depend on gravity. So we're going to look at how circular motion principles can be applied to practical problems. So, effects of zero gravity on the human body. Balance is the first one. Okay, how do you keep your balance? What part of your body is responsible for your balance? Well, your legs are what you stand on. That's what keeps you standing. Your core helps you. Something is sensory. What's sensory part? Your ears. Yeah. In the middle ear, the inner ear, okay, are the little semicircular canals right behind the cochlea. That's the one that's shaped like a seashell. Okay, and in there is essentially your balance center. Okay, there are little cells in there that look kind of like hairs and things that are kind of like grains of sand. And when you turn your head, gravity pulls on those little like grains of sand, and they stimulate the little hair cells that tell your brain, oh, you're leaning. Please tell the core and the right leg to rebalance and contract and keep you from falling over. Okay? If you get, like a bad ear infection, one of the effects of that can be dizziness, okay, and a lack of balance, because there's inflammation around that organ that interferes with its ability to work. Okay? It can also cause you to feel nauseous, okay? Especially if you're like on a roller coaster ride and you're being thrown around in different directions. Those cells in that sensory organ gets really confused because it's constantly being stimulated and you're all over the place, and it tries to figure it out. And that's what can cause some people to be more sensitive to motion sickness than others. Okay? And sad story, it gets worse with age. Okay? Every time we used to go on the trip, I would go on every ride and ride all the rides as much as I can. And now that I'm getting older, I can't. Okay, just that organ as you age just doesn't work as well. You become a lot more sensitive to motion sickness, right? And I don't want to be the guy throwing up. I've been there, done that. Okay? I don't need to do the technicolor yawn in front of everybody. Okay, like never recalled that. Okay, so things that can happen in the human body to your balance center. If you go into zero gravity, you start moving your head around, okay, those things that depended on gravity to tell you which way was up and down no longer work. In fact, it's worse than they no longer work. They're like that car alarm that's always going off. Okay? They're constantly telling the brain, oh, you're leaning, you're falling, you're leaning, you're upside down, you're right side up, you're sideways, okay? Because those little grains of sand are just going everywhere. Okay? And it doesn't understand, your brain doesn't understand what the ear is trying to tell it. The first few days in zero gravity for astronauts are really difficult. They often are very sick. Okay? They're very nauseous, very sensitive to movement and things like that, because their brain is still listening to the middle ear. Okay? Now eventually, your brain does what you do to that car alarm that always goes off. You just kind of get used to it and ignore it. Okay? And eventually the brain stops listening to the balance center in the middle ear. And instead it relies on your what? Your eyes. Because your eyes can kind of tell it which way is right side up and which way is upside down. So it starts to rely on those. And that works fine in zero gravity. The problem comes when you go back to a gravity environment. When you come back to a gravity environment, you're standing on the ground being pulled into the floor is pushing back. You turn your head like this, Your brain, which has been relying on your eyes, says, oh, we're falling, okay? Because the head's going that way, we must be like moving towards the ground, and it'll cause you to fall down, okay? That's why, if you've ever seen astronauts, when they used to have the space shuttle, okay, they would put the ramp up to the space shuttle and have these handlebars on either side of the ramp. The astronauts are doing gripping those, white knuckle. And then they're actually escorted with one person on each arm down the long hallway, okay, until they can sit them down somewhere. Because if they don't, and someone says, hey, Chris, over there, and they look, they'll just walk that way and they'll fall down, okay? Because their brain has become so used to using the eyes for balance that any movement in the eyes causes the whole body to go that way, okay? Everyone kind of follow me there? Okay? That can be bad. If you've been on a spaceship going to Mars for 6 or 8 months, your brain's all used to using your eyes for balance, and you have the honor of being your generation's Neil Armstrong and putting the first footprint on Mars. You get to the top of the ladder, look down at the steps, and fall down the steps. Clunk, 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 break your faceplate, die. Okay? So you leave the first, like, print, okay, on the surface of Mars and a not-so-beautiful course. Okay? So we don't want that. That's dangerous. Okay? That would be bad. Chris Hadfield actually had, when he got back off the International Space Station, he'd been up there for 8 months or something like that. Okay? When he came back, he was doing a driving simulator. Okay? And anytime there was a stimuli on one part of the screen, he would look over there and he would drive right towards it. Okay, drove off the road, okay, all that kind of stuff. It takes a long time for your body to start listening to the ear again. Okay, so that's one thing. That's just one thing. Okay, the fluid in your body gets redistributed. In a gravity environment, fluid tends to go downwards because gravity pulls it. So it winds up in your feet and your lower extremities. In zero gravity, it redistributes equally. And for a lot of the time they're in space, astronauts will have more arthritic pain because there'll be more fluid in their fingers and hands. Okay, they'll actually be swollen, especially the first few days. They'll look swollen in their face. It'll actually look like they've gone a few rounds. Okay, it's bare knuckle boxing because they'll be all swollen. Fluid redistributes to the face, and they tend to have a much more nasally sound to their voice because they are congested. The fluid moves into the sinuses instead of draining away properly. Other things that can happen. Since you're not in a gravity environment, how hard do your muscles need to work? Yeah, they're not bearing your weight all the time. We don't even realize just how much your muscles are always working, like your core is keeping you balanced, all that kind of stuff. In zero gravity, it doesn't need to do that. So your muscles begin to atrophy, okay? Including the muscles that help you breathe and your heart. Okay? Your heart can actually be significantly deteriorated if you're in zero gravity for a long period of time because it's pumping blood that's weightless. It requires no effort at all to pump the blood to your head anymore, okay? Because the blood doesn't weigh anything. And so it can be, your heart can actually start to atrophy if you're in zero gravity for too long. And the muscles that help you to breathe, the ones in your rib cage, your intercostal muscles, okay, the diaphragm, all of those things not working against gravity get weaker. And when you come back to gravity, you can tire easily. It takes a while for you to recover those muscles. And it actually happened to some Russian cosmonauts, Soviet actually, cosmonauts at the fall of the Soviet Union. They were up on the Soviet space station Mir. And when the Soviet Union crumbled, they got stuck up there. Because the Soviet Union was gone, there was no money to go back and get them. And of course the Soviets didn't want anyone going to Mir because it was kind of still theirs. Like, well, the Americans like, hey, we'll go get them. Take a look at all your stuff up there, okay? And of course the Russians wanted none of that, so they wouldn't let anyone do anything except send supplies. So these guys were stuck on the space station like over a year. When they came back, they could barely breathe. Right? They had to be put on supplemental oxygen until the muscles in their chests got strong enough to actually ventilate their lungs properly. Okay? So extended periods of zero gravity are pretty hard on you. Okay? If your bones are not being used to bear weight, your body will recycle them. Okay? You ever see what happens to people when they get elderly? Right? They kind of get hunched over, they get osteoporosis. That can happen to you in zero gravity. It happens because your body's realizing your bones don't need to be that thick. You're not bearing any weight. Okay? So as a result, it'll start to pull the calcium out of your bones, and your bones will become more porous and more easily broken. It can also lead to high levels of calcium in the blood, which then has to be filtered by the kidney, which can lead to kidney stones. Okay? Now, on Earth, kidney stones are inconvenient and exquisitely painful. In space, they can be fatal. Okay? You are a long way from a hospital if you are on your way to Mars. Okay? Getting something like a kidney stone that could cut up your insides or cause an infection or something like that can be pretty serious. Okay? So there's all kinds of things that can go on, okay, in the human body in zero gravity. One of the ways to counteract that would be find some way to generate artificial gravity. Okay? We know there are ways to do that, but building a ship that can do it is a little more difficult. Okay? The idea is sound, it's work, but having the technology to do it is kind of a stumbling block. All right, so we're going to look at quite a few videos here of what it's like to be in zero gravity. And Chris Eppiel had like a whole playlist of videos from his time on the International Space Station. Some of the things they encounter, difficulties they encounter being in zero gravity. So we'll have a look at those here. Okay, so how do we combat that problem? Well, we make at least part of the ship, if not the entire ship, a spinning drum. Okay? If we have a spinning drum or part of the ship that's a cylinder that can spin, okay, we can create artificial gravity using inertia. Okay? That works like this. If I have the spinning drum, like you've seen on a lot of science fiction movies, okay, a person standing on the inside of that drum, their inertia wants them to do this, go in a straight line. But because they're standing on the inside of the drum, what happens? They get pushed into the drum. They get pushed into the ground, right, the floor, okay? And they get pushed into that, and then what does the floor do? Pushes back. That's what gives you that feeling of artificial gravity. It's not gravity at all. It's normal force. We're just using inertia to create a force that pushes against the inside of the drum, so the drum will push back towards the middle, and will feel some gravity. Okay? If I'm not against that, okay, then I'm not going to feel the gravity. Okay? If I'm on a ladder or something like that going towards the center, I'll feel gravity. Okay? But if I could just kind of float freely, okay, around in there, as long as I wasn't also moving with the cylinder. Okay? As long as I'm rotating, I'm going to travel towards the outside of the cylinder in a straight line. Okay? Does that sort of make sense to everybody? Okay, so I'll actually show you a couple of videos where they have that in there from an actually very old movie. It's even older than me. They actually had movies then. Okay, but it's actually a lot older than me. Okay, where this idea was used as part of the movie, and the sets and special effects were incredible because they were actually practical. They weren't CG in any way. Okay, so this is what we use. Okay, we have normal force. We have normal force providing a centripetal force. And we want that normal force to feel like what force? Gravity. How do we calculate force of gravity? M times G. Okay? Okay, so artificial gravity works just like this. I want gravity to feel like centripetal force. Or the other way around. Okay? And then I can solve for things like how big does the station need to be, how fast does it need to move if I want to feel like I'm at home on Earth or something like that. Okay? If you were headed to Mars, you wouldn't necessarily need to have this running at full Earth gravity. In fact, you might want to get used to Mars gravity, have it run at about 1/3. Okay? On the way back, you would probably crank it back up to Earth gravity, or maybe you want to look good on the beach when you get home, crank it up to 1.5. Okay, and you're a little heavier. Everything's a little heavier. You get a good workout just by moving around. Okay, and you would build up that muscle mass again. Okay, so the surface of the station provides that force by pushing on the feet of the astronaut, because the astronaut's inertia makes them push against the inside of the drum. Okay, the centripetal force can be adjusted to match the astronaut's earth weight by properly selecting the rotational speed of the station, okay, as shown in an example we're going to look at here in a minute. So this is actually a shot from 2001: A Space Odyssey. Okay? Very old science fiction movie, but it's still, like, if you watch it today, I'm going to show you bits of it today. Okay? The special effects don't look all that bad. Okay? But what they had to do was build a rotating drum. Like, this set was actually built like this, and it rotated. So these guys would show them with the drum rotating, and they would always be on the bottom of it. But they'd let the camera rotate with the drum. So it would look like they were upside down and things like that. It looked really cool, even though they were always on Earth, using Earth gravity, just walking at the bottom of the drum. Okay? The only problem would be when one of them was sitting at one of these stations. they would actually have to seatbelt them in so that when the drum rotated them upside down, they didn't fall. But the whole set actually rotated. They also have one, the first scene I'll show you is they have a big space station that's just a big wheel. Okay? And that big wheel spins, you can see the set that they built. And you can kind of see how it wasn't like a real space station because you can actually see when they're walking downhill and uphill in the set that they built. Okay? Because this one actually didn't rotate, it just was curved. You know how you look when you walk downhill, right? Like you lean back a little bit. When you're walking uphill, you lean forward a little bit. You can actually tell if it's down. Okay, so what we're going to look at here is we're going to do like a sample problem to do with artificial gravity. And I can't remember the last time I didn't put an artificial gravity question on a unit exam. So this is probably one you want to pay attention to. Okay, we want to figure out what speed the station needs to rotate at, or this drum needs to rotate at, if it has a radius of 1,700 meters. So it's huge. Okay, what speed does it have to move at so that the astronaut feels a push on their feet that is equal to their Earth weight? Well, what we said a minute ago was that normal force is providing the centripetal force, and we want that normal force to feel like gravity. So we say that m times g equals mv squared over r. We want it to feel like they're at home. Okay? What we're trying to find is the speed. Okay, so I want to get v by itself, so I'm going to multiply both sides by r. What's going to happen to m? Okay, does that make good sense? Everybody should feel like they're at home in this station, regardless of their mass. Okay, and v is going to be like that. So we're going to have that v will equal the square root of GERT, not mu GERT. It's different. Okay, this is GERT. All right. So now that we have that, okay, v equals the square root of acceleration due to gravity at home, 9.81, times the radius of the station, 1,700 meters. So square root of 9.81 times 1,700. Is this thing going to be moving kind of fast? Yes. Okay. The bigger the station, the faster it has to spin in order to feel that kind of gravity. So the outside of this station would be moving at 130 meters per second. That's really fast. Like you would not want to try and like walk on the outside of that, okay, or try and grab onto that. Okay? If you were doing an extravehicular kind of thing, okay, it would be very dangerous.
Wouldn't the hertz be slower though?
The period would be longer. The hertz would be yes. Yeah. Okay. It's a matter of, but it's still a matter of speed, right? Yes, because of what it's doing, the period
So
would
that
be longer.
the whole thing would be like, rotating slower, but the end would be going faster.
Actually, all parts would take the same amount of time to go around, right? So I see what you're saying here. Out here, the period would be like, let's just say, I don't know, let's say 10 seconds. Well, the period here also has to be 10 seconds because they're attached, right? That's why out here you're moving faster because you're going farther in the same amount of time, right? This circle is bigger than that circle, but they have the same rotational period or the same frequency, okay? And well, that's what we were talking about in the lab. Does that make sense? All right, does everyone kind of follow how that works? Okay, so in The Martian, when that scene where they were docking with the Chinese spacecraft that was bringing all the supplies for them, okay, one of the guys was doing an EVA, and he actually went past the rotating part, tried to grab onto it, and it was one of the most dangerous parts for his maneuver because if he misses that, okay, then he could float away, and it was moving very fast. Okay, so you have to be mindful of that. Probably if you were doing any maintenance on the outside of this part, you would turn off the rotation, at least temporarily. All right, so the Earth weight of the astronaut we calculate by going m times g. We substitute that in. Then we have mg equals mv squared over r. And we get that the thing would have to rotate at 130 meters per second. Right? So this is the idea behind what are kind of called like generational ships or long-term voyage ships. Arthur C. Clarke, the guy who wrote 2001: A Space Odyssey, the book, also wrote a series of books about a cylindrical spacecraft that traveled through space and had this, that it rotated and it created gravity on the inside because of this rotation. Okay? And this is kind of what it would look like. Right? We'd have a cylinder, actually at the end of Interstellar, same thing. They have a really big ship that's spinning, and you can see in that scene where they hit the baseball and break the window, the whole thing kind of goes up and away. Right? So if you build this big cylinder, then you would have this entire internal area where you would have gravity. It would feel normal as long as you kept it spinning fast enough. Okay? And obviously, you could have all kinds of like normal Earth-based types of things. You could have, crops growing, fields, whatever. Okay, your only issue would be light. Okay, and so you'd probably have to have parts of the cylinder that would be lit. Okay, like projecting light onto the other side. Okay. Now, there would be one difficulty though, and it has to do with cycling the water. And you have a big contained environment like this. When the water cycle is going, water evaporates and it goes up. Okay, but it can only go to where? Yeah, well, or to the center. Okay, so what would you have at the middle? Yeah, you'd have a cloud. Okay, you'd have to have some way of like cooling the center of that so you can condense the water and have it fall back down as rain. Here's the weird thing: the rain wouldn't do this. It wouldn't fall straight. It would fall like this. Okay? And in fact, if you did any accelerating or decelerating, all of the water contained in the middle, okay, would shift towards the end. And then when it hit the end, because the end is spinning, and there would be a Coriolis effect, if you remember that from Science 10, okay, you'd have a curved waterfall at each end of the ship. Okay, so water would be going down this circular face, but it can't fall straight because this is spinning, so it would do this. You have a curved waterfall. Okay, at the end, the rain would fall in curves, really funky whack. Yeah. So there'd be some weird things, but other than that, it would seem pretty normal. All right, so that's all the stuff to do with artificial gravity. Now tomorrow we're going to be doing another lab, but this one's going to be on centripetal force and speed, whereas our last one was on radius and speed. So it's essentially the same procedure, except instead of changing the radius, we're going to change the mass that's hanging at the bottom so we can change the centripetal force. Okay? And then kind of performing a similar thing. So if we stay focused on that, it's again not one that should involve a whole lot of homework for you. You should be able to get it mostly done in class. Okay?